Buongiorno, everybody. It's a great pleasure to be here, and thank you very much for the kind introduction. So I will start by introducing myself a little bit. I come from Paris, and I'm a researcher. Actually, I'm a strange kind of a two-headed beast, like this guy from Sesame Street, because during the week and at work, I'm a physicist. So is it working okay with the microphone? It's yeah, okay. So I do experiments on glass, like window glass. This is the research topic of my lab. But during the weekend and at night, I'm also a hacker, a geek. And I've been working with Python and scientific Python for more than 10 years now, and I'm a contributor of the scikit-image module, which I'll be talking about. It's an image processing module. So we're at a Python conference. I don't need to tell you that Python is a hugely popular language, but I'd like just to give a few figures to measure this success. And so since I've been using Python for 10 years, I know that at the beginning it was really considered as being a bit weird to be using Python. It was, oh, you're very geeky, what the hell are you doing, instead of using MATLAB, for example, which was very used in my field. But now you see on this graph that in the top tier US universities, Python is now taught as the introductory programming language. So it's really mainstream now. I think you can also see this from the number of people who are attending this conference. It's not something very confidential, something very small and geeky to be using Python. So this plot is taken from the computer science departments in US universities. So I'm more into the physics and engineering fields, and I have to say that in engineering departments, maybe the situation is not so good, because things might be changing a little bit less fast than in computer science. And the reason might be that academia is not a field that is known for its innovation in terms of tools and processes. So I've taken here two citations from famous physicists, Max Planck and Einstein. So it's very sad I'm not sure I completely agree with what Planck said, science advances one funeral at a time, saying that things only change when just someone who had a lot of power on a field and was imposing the tools just has to leave because of various reasons, which might be a funeral. But academia is still built with very famous professors that impose their tools, and therefore it's a bit harder to introduce new tools. However, the situation is still quite good, because even very traditional, well-established institutions like the Nature journal have become to advocate Python. You see here this article on the Nature website, programming, you should pick up Python, and why? Because it's a powerful programming language with a huge community support. So I think that when even Nature say that, I think the battle is almost won. And so during this talk, what I would like to talk about is, why is Python a popular language in science? So I'll really focus on science. It's really great that in this conference here you have people from a lot of different fields. I also don't know about your backgrounds here in the audience, so I don't know how many people here are working, are like engineers or researchers or using scientific Python. Okay, I would say half of the audience. How many people are more into web development or system administration? So it's quite a diverse audience. It's very nice. And so I'll give a lot of illustrations taken from Scikit-Image because it's the tool that I know most. It's the one I'm contributing to, so an image processing tool. But I like to focus on two different aspects about the development of these tools. The first one is how to choose your API so that it will be simple enough for users. And the other one is how can you be creative with documenting tools so that the life of your users is easier. So what I won't be talking about here is the reasons for success of Python that are common to other fields than science. And for example, in this famous XKCD cartoon, I'm sorry, the resolution is really not good, but the fact that the syntax is very simple. Hello world is just print hello world. We all know that it's a great aspect of Python, but I think it's great in all fields where science is used. And so the syntax, the simplicity, it's not something that I will be talking about in this talk, but of course it also contributes a lot to the success of Python in science. So I'll start by introducing what is Scikit-Image, and of course I have to introduce this in the context of the scientific Python ecosystem. So what is scientific Python? It's a kind of umbrella word that we're using, and it really means Python, the language, its standard library, together with NumPy, the module for numerical arrays. And on top of this two very important tools, there is a large variety of other tools that have grown on this foundation. You have, for example, all the different signal processing modules that are very important in science. You have more specialized modules. For example, I'll be talking about Scikit-Image, which is for image processing. You have visualization tools for 2D, for 3D, and you also have tools that you're using to interact with your code, like interpreters, IDEs, and it's a great aspect of scientific Python that it's so modular, and you have a lot of different tools, but first-time users might be a bit at loss, thinking, okay, which one am I using? Am I using Python? Am I using SciPy? What's the big difference? And fortunately, there are also distributions that bundle all these tools together so that if you don't want to think too much about it, you can just install Anaconda and so Canopy, and you have everything with batteries included. So that's what most engineers and scientists will do. And so Scikit-Image is one of these modules. And so let me just say a few words about NumPy. So who is not using NumPy here? Just to have an idea about... so everybody's using NumPy, right? It's okay. So that's quite comforting to be sure about that. But for example, I know some curriculum in French in undergraduate studies where they study Python, but they don't cover NumPy arrays. They use list of lists, which is really, really silly, right? But it's the kind of illustration where I'm saying that things still have to evolve. So this NumPy object, it's something that has really been polished through the years, and it's this multi-dimensional numerical data container, and that has different dimensions, 2D, 3Ds, and it has very efficient data access because it's an ordered view on the memory of your computer. That's very important. And it also has this versatile data access because you can, of course, do slicing, but also fancy indexing. You have very powerful methods to access the data. And of course, NumPy, it's not something that we want to be thinking of because it's a commodity for us when we're using scientific Python. But the the fact that this object is so well thought and so well realized, it's a huge reason for the success of Python. So on top of the object, you also have a lot of utility functions, either to create or to manipulate the arrays. I've put just one here, the one to create random integers, but you really have a lot of functions, and even if you're using scientific Python a lot, you keep on discovering new functions in NumPy. So moving on to scikit-image, I also thought that it might be interesting for this PyData audience to talk a little bit about image processing, because when you're thinking about data, images are a very important type of data nowadays. And why? It's partly due to a revolution in microelectronics with very cheap CCD sensors, so that nowadays if you want to buy a CCD camera, it costs nothing. You have really good ones on your cell phones, and everybody, really everybody, even kids, are taking a lot of pictures, uploading them on Facebook and all kinds of social networks. You can see from this graph that 500 million images are uploaded on Facebook every day. So, and of course the Facebook guys, they want to take advantage of all this data. So there is a lot of work for image processing. But image processing is not only useful on social networks, it's also very important in science, because this cheap CCD or CMOS sensors, these cheap cameras, they are also very useful for science. And here I've taken an example from solar research, where they have cameras looking at the sun, and every day they have terabytes of data that are recorded. And of course, you cannot have a student looking at each image and seeing if something interesting is happening. You need automated data processing, image processing. So I would define image processing as taking an image and manipulating it in order to retrieve either new other images or some characteristics of the image. They can be features that you can use for automating detection. They can be measurements that you need to understand the science of your process. And image processing is also very often combined with machine learning, for example, for automatic detection. So scikit-image is an image processing library. Here are a few characteristics of the library. First, it's open source. It's BSD licensed, so very permissive. You can basically reuse it for everything you want. It's a library, meaning that it's not an application. So it's not something with a lot of visualization, for example. It's meant for you to reuse it in other situations, to adapt it to your framework. So it's for Python and NumPy, and compared to other image processing libraries, it has a specificity that it can handle both 2D and 3D images. Because you have other very nice tools for image processing in Python. You may know OpenCV, for example, which is a really cool package. But the fact that scikit-image can handle both 2D and 3D arrays is a bit specific, and it's really due to what the NumPy array can offer. And another specificity is that we strive to have an API that is as simple as possible and a gentle learning curve. So scikit-image really targets users that want to learn in a gentle way, like students who after will become engineers, researchers, but that don't have a lot of help when they begin, and people for whom it's not their job to be a programmer, like biologists, physicists. And so we would like them to learn as fast and as well as possible, but of course also to be able to do advanced things, not only to do the basics. So a few statistics about the package. We're at release 0.12. We have 1 or 2 releases per year. And you can see here in very small the statistics of download on PyPy. You can just see that it's increasing in a nice way. And as a measure of the number of users, it's actually very hard to know exactly how many users you have when you have a package. I like to take a look at the number of unique visitors on the website, on the documentation website that we have per month, and it's about 20,000 visitors per month, and it's increasing. So why is scikit-image relying on NumPy arrays? Well, first, because NumPy arrays are a very natural object for images. An image, it's a collection of pixels with a spatial order, and you already have this structure within the NumPy array. You can see on this example that if you create a 2D array, you can consider every element of the array as a pixel, and with NumPy it's very easy to change the value to access the elements of the array. So we'll really, I'll be talking about arrays, images. It will be really the same when I'm talking. And so here you have an example of a 2D array, but so this was a black and white array image, sorry. But when you have a color image, it's just a 3D array where the last dimension is color channels. That's all. And if you want to go to 3D images that you may encounter, for example, in medical imaging, in MRI, in CT, then okay, no big deal. It's just a 3D NumPy array. So the correspondence between an image and a NumPy array is very natural. And therefore, in scikit-image, functions use NumPy arrays both as arguments and as outputs, as you can see here from this example. So here is my first bit of code in the talk. So what we start with importing submodules from scikit-image, schemage. And so we read an image from a file. And so this camera array object, what is it? It's just an NumPy array with data type that is an unsigned integer on 8 bytes. And when you have this array object, then you can apply functions of scikit-image on this object, like this Gaussian filter. And what you see is that the object it returns is also an NumPy array. So it's a syntax that strives to be as simple as possible. Input is an NumPy array. Output will be an NumPy array as well. And so the syntax of scikit-image functions, it will always be like that. That is, an image processing operation, it will be a function. And the first input, it will be an NumPy array. And you might have additional parameters that will be keyword arguments. So here again, we make heavy use of a cool feature of Python, which are the keyword arguments, because often when you're doing image processing operations, you have parameters that you might want to fine-tune, but not at the beginning when you're starting your image processing workflow. And you really don't want to be bothered with them, so you just hide them in keyword arguments, and when you really need to fine-tune your workflow, then you can modify them. I would like to say that this simple API is not something that we've always had. Like if I go back to 2013, when you were reading an image from a file and you were asking for the type of this object, the answer was not NumPy array, but some image class. This image class, it was nothing else than a very simple wrapper around the NumPy arrays with a few additional parameters that were okay, a bit nice, but that were really not useful. And it was very confusing for the users, actually. When do I have an NumPy array? When do I have this image object? And after, when you were applying simple NumPy operations, like asking for the maximum value of your image, you had an even stranger answer, like you didn't have a scalar answer, you had an image, again, this image class. Okay, so at some point we really were not happy with this image class, so we just ditched it. And okay, we didn't have any more the nice arguments, the nice parameters of the image class, but the benefit of keeping the API very simple was definitely worth it. So now we only have NumPy arrays. I would like now to take you through a quick tour of what you can do with scikit-image, and I'll also show you how I use it for my daily work. So in scikit-image, functions are organized in submodules, and for example, you have the filters submodule, which allows you to transform basically your image data. And you can transform image data either according to the values of the neighbors of one pixel. That's, for example, what's used in denoising filters. But you can also filter only the values of the histogram when you want to change the contrast. You can filter an image to go from objects to their contours, to their edges. And so all of these operations are found within the filters submodule. So I would like just to show you how I typically use this filters module. And here I have a small movie of a typical image that I'm getting during my work. So this is a movie of what's called phase separation. So phase separation, it's what happens when you put together oil and vinegar. It's two liquids, they don't like to be mixed together. And so here on this movie, I have represented the surface of one of the liquids that's evolving with time. So it's, I don't want to delve into the details, but it's not oil and vinegar, it's liquid glass at 1000 degrees actually. This is a kind of object that I'm studying. And so what I would like to know is how is the morphology of the surface evolving with time, because it has some consequences for the industrial applications where you're using this phase-separated glass. So this movie, it's what you can obtain after image processing. That is when you have separated the two phases and you can plot the surface. But what you're starting with is not something as simple. Because we're doing the experiments, so it's experiments, it's not simulations first, and we're doing the experiments in synchrotron, it's a source of X-rays, and then we're trying to image the sample as fast as possible because it's heated, it's evolving fast, and therefore what you get is this kind of noisy images. So it's 3D images, so here it's a cut through the image. And you can see here that even if you would like to have only two phases, the black and the white, you have a lot of noise. So to be able to separate the two phases, you need to apply filters and denoising filters. So here I've represented the output of 3 different filters. The first one is the median filters. It's a very easy filter. It's I would say the least known secret of image processing, that before doing any segmentation, you should do simple filters like a median filter, because your image already looks much better after median filtering. But you can also use other filters, and for example, the total variation filter, it's a filter that's very well adapted to black and white images, because it will give you images where regions are piecewise constant, that is, they have almost constant gray values. And that's why I'm saying that some filters, they are adapted to a very wide class of images, like the median filters. Other are more specific. And the cool thing is that you have a large variety of them in scikit image. So here I just plotted the histograms of the pixel values after the filters, because that's what you can use to separate the pixels belonging to one class or the other. And you see here this big potato-like histogram. It's the original image, so it's very hard to say, okay, where is the threshold between black and white? But after you do only the median filtering, it's already much better. And after the total variation filter, your peaks are even more defined. So all these functions that you can test, you can use them with each time it's one line of code. And here, for example, you see that I've used the bilateral filter, and then I was not completely happy with the result, so I played a little bit with the keyword arguments. That's what I was telling you. Keywords arguments, you can use them to fine-tune the result. And the total variation TV filter, it's also the same syntax. So you see here that all these filters, denoising filters, they are starting with the denoise word, and it's actually something that also has evolved through the API, because before you had bilateral function, you had a TV function, and it has actually taken some time to impose a coherent API like this in the restoration module. You have different filters for restoration of your images, but all the denoising filters, they start with the denoising, except this one, but it's deprecated because it was the original name. And when we switched to the name coherent with the rest of the API, of course, we're starting to have a lot of users, so we don't want to break the API too quickly. And so we need still to keep these names in the API. It's a pain. And therefore, it really tells you that if you can take the good decisions on the names of the functions, even on, about the names of keyword parameters, to have some coherence through your package, it will save you a lot of time and a lot of discussions between developers afterwards. But of course, it's not something easy to do, and sometimes you just have to bite the bullet and break your API and keep deprecated names for 1 or 2 releases, and that's it. So after you've done segmentation, you've done filtering, you can go to segmentation of your image. So what is segmentation? It's a task of attributing different labels to regions of the image. Like, for example, here you might want to separate the cup from its background, or here to separate the astronaut from its background, or the text, and so on. And once again, you have different strategies for this task, depending on the gray value statistics of your image, whether the contrast changes through your image or not. And you also have a large class of methods in the segmentation submodule of scikit image. And so here is once again a little movie from my work. So I study also how glass is created at high temperature in furnaces. So I don't know if you knew that glass is made out of sand. And so here are some sand grains. And it's not only made out of sand, but it's you also use other chemical species to react with the sand and to create a liquid. And this is what happens here. You have one grain of carbonate that reacts with the grains of sand. And we're again using this in situ 3D imaging technique to take a look at the geometry of the reactions to see which are the parts of the mixture that react first. And for this, of course, to have some quantitative insights into the process, you cannot just look at the images. You need to measure like the volumes of the grains that are reacting. And here is a typical sequence of the workflow that I could be using for this. Like I have this very noisy image, but I can do some denoising using this non-local means filter that preserves very well the texture. So it's once again a specific kind of denoising filter when you have a fine-grained texture and you want to keep it. And after, I will use a region propagation segmentation technique. Like I have some markers determined by the histogram, and they will propagate through the image, and at the end you have a quite good separation. So here it's from the background, between the background and the images. And after, of course, you can also separate the grains that are touching and so on. So in general, you don't do all the segmentation in one pass. You segment the objects from the background and then the different objects that are glued together. But all this can be done within scikit-image. There is also a mathematical morphology module, which can be used, for example, for cleaning your data, because of course you would like to do everything with one function, like one function that would do the denoising or the segmentation for you, but sometimes the result is not perfect. And so the mathematical morphology function, they can be used to remove very small objects and to improve the result of your segmentation, for example. Something that might be of interest to this audience also is the feature submodule, which is used to extract features out of images, features that can after be used in a machine learning algorithm. And so this feature, they can be geometrical characteristics of your images, like corners, lines, but they can also be statistics about local values, local gray level values. And you have quite a large number of feature detection methods, although the documentation could actually be better for this module. But so here I'm just showing you a quick example where segmentation was done. So segmentation of this nice animal in the background. It was done not by some classical image processing segmentation algorithm, but using a random forest classifier, so a typical machine learning algorithm, which is the random forest classifier of scikit-learn. You have talks about scikit-learn also in the PyData schedule, right? Or yeah, just to be sure that everybody here knows scikit-learn. Yeah, okay. But first, when you want to use a classifier, you need to have features, and this is where the functions of a scikit-image can help you. And for this image, the features, they were quite simple because they were mostly statistics of the local gradients. But you also have more advanced descriptors, like Gabor filters. We're starting to have wavelets as well. And then you can classify pixels. So this combination of both scikit-image and scikit-learn, it's also something that comes completely for free with the scientific Python ecosystem, because since the two modules are using NumPy arrays, I mean, you can plug the output of one module into the input of another one. It's completely easy. You just have to know that it's possible to do it. After you have done the segmentation, you have isolated some regions of interest, you often want to do measurements on images. And in particular, we have this region properties function that permits to compute statistics about labeled objects. Like, for example, these coins, you want to know their bounding box, the size, and so on. So all this is already coded. You don't have to code it again. And well, of course, I could spend more time detailing every submodule of scikit-image, but it could be a bit boring for you. So what I suggest, if you want to know more, we have quite a comprehensive documentation on the scikit-image website. And so I just like to go back about this API questions. So to summarize the API of scikit-image is that you have submodules and then functions are found within submodules. We had some heavy discussions between, well, heated discussions, I would say, between developers because some people thought, okay, why don't we have everything under the scikit-image namespace? But then it could be harder to discover a function just using the tab within IPython. When you're in the restoration submodule, for example, sometimes you can just discover a new function just pressing tab because everything is quite nicely organized. So for now, we're keeping this submodule architecture. And when you have a function, its variables are as input an input array, and as output, it's also an NumPy array. And of course, you can have optional parameters that can have various D types, but it's usually just scalar values, like numerical values. So this is for really most objects in scikit-image. We have a tiny number of classes as well, like this MCP. I don't even know actually what MCP stands for, I'm afraid, but it's a minimum cost path. Yeah, thank you. Thank you for the help. And so it's something that's actually used also in functions of the graph submodule. And I was just checking the documentation visits, the website visits. This is a page that's never visited. So I really have the impression that as long as you keep the simple API, people will use the objects. But if you have more complicated objects and if they are not used consistently through your API, then it's really a disadvantage for these objects and they might be useless. So consistency through the API is very important. And I'm really not saying that it means that you need to have only functions in a module. This is absolutely not what I'm saying, because for example, if you take the scikit-learn module, it's really famous for its ultra-clean API with models that are objects, but all of them, be them models for classification, for regression, for clustering, they have this fit method for the training step, and then this predict method, and they all share this common API. And as long as it's used consistently, which it is in scikit-learn, then it's not a problem to have a class. So don't take me wrong, I'm not saying that classes are bad and functions are good. I'm just saying that you should try to have as little variety in the API of one module. And this is really what we learned through the years. And so still on APIs, but on a slightly different subject, I'd like to show you that the possibility of using both 2D and 3D arrays in scikit-image, it's really something that we inherit from NumPy. Because you can see here on this snippet of code that when we want to label connected components on an object like this, we use exactly the same syntax for a 2D image or a 3D image. So this is something that's very nice because, for example, I'm using 3D imaging for my work, but I have colleagues that are working a lot with 2D images, like from microscopy images, for example, but we can use the same functions, we can share some code. It's really easier to interact together. And of course, it's because this object, this input object, since it's a NumPy array, it can be either a 2D or a 3D array. And of course, we could have inside the functions, like we could test cases. If the dimension of your array is 2, you do this. If it's 3, we do this. But NumPy provides more elegant methods. For example, this np.atleast3d method, functions, sorry. So that in a lot of functions, actually, we're just considering that all images are 3D, and then if we had a flat dimension, then it's no big deal. It will be completely transparent. So it reduces the number of code lines that you can have when you want to support both 2D and 3D arrays. And it's not something that you need to develop yourself. It just comes with NumPy. So it's very nice. A few words about the development model of scikit-image as well. So since the package is well, quite mature now, we are trying to be a really stable package. That is, we will only include mature image processing algorithms. Sometimes we have people who are very enthusiastic, who come to GitHub and who say, I have this very powerful image processing routine. I developed it during my PhD, and it's not published yet, but it will really improve the segmentation by orders of magnitude. And then we say, okay, I'm really sorry, but it's not possible within scikit-image. You should create your own package, and then maybe you'll have users, and you will have some bug detection and so on, because when you have code that has not been published, then you're sure that you will find bugs usually. And one specificity is also that we have only Python and Cython code. There are other very powerful, very complete image processing libraries that rely on C or C++, and that have really good results. But since we're trying to have a lot of developers and to have a good maintainability, for the trade-off between maintainability and performance, sometimes we go a little bit to the side of maintainability, because on the long term, we think it will be better for the package. Like the other modules of scientific Python, we put a lot of emphasis on good practices. Like all of code has to be tested, it has to have a lot of documentation, and so on. So the core team of scikit-image, it's composed of 5 to 10 persons, I would say. And so all these core developers, they are people who are using scikit-image for application. They are not computer scientists. So it's also a good way to be well aware of what users will want if you have the same problems as user. So you can see here in very small, I'm afraid, the faces and the names of the core developer. The main developer is Stefan van der Walt, who you may know. My only regret is that there are not enough girls in this team, so if some girls, or some guys also, of course, are interested to join, it would be great. But it's a quite healthy community of developers. We had, for the last release, last month, we had contributions from 60 people, so it's, of course, ranging from very small changes to major changes, but it's nice. And you can check that it's indeed quite a healthy community by looking at this graph. So I made this graph using a script from Fernando Perez. And so what he did was to do statistics about the Git log. And for each package, so each plot, each curve is a different module. And one is the number of commits of the top committer. And after the all the different numbers of commits are normalized by this maximum number. And if the curve is decreasing very fast, it means that you have basically one user who's contributing a lot, and that the so-called buzz factor, what happens when this user disappears, is very small. So for a healthy development means that you should have a curve that doesn't decrease too fast, like scikit-learn has a really a crazily healthy development. But scikit-image is here it's the magenta curve here. It's quite good too. I was saying between 5 and 10 core developers. Here, for 20% of the top committer, we have 8 users, which is quite good. So all this top contributors, although they are using the package, there are also people who are quite advanced users of Python. And this might not be the case of all users of scikit-image. So I think it's very important when you are a developer to keep thinking, who is my typical user? What will he or she want to do with the package? Because, of course, this is what you would like your users to look like. Very strong JEDIs, and, of course, also very gender-balanced JEDIs, but this is another issue. And when you take a look at the data, it's not like this, of course. So I took some statistics from our website analytics, which we are using pWeek for this. I thought that only Google Analytics could do a good job at this, but a developer of the package convinced us that no, we should use an open source tool for this, and pWeek is actually quite good. I was completely against it at the beginning. I thought, oh, okay, no, we should use Google Analytics, but you might want to give it a try with pWeek. It's also quite nice. And so here are some statistics about typical users of scikit-image. So first, which OS are they using? So in this room, I can see a lot of Macs. I guess other people are using Linux, but when you take a look at the statistics, we have 54% of people who are using Windows. So it might be a bit hard on Windows users to say Windows users are not as geek as others. Of course, it's not true, but if you want to use something as a proxy to the level of geekiness of your users, it might be not so bad. And of course, there are people who don't have so much time, because so here it's the histogram of time that people spend on the website. And so you see that so every day we have 1,500 visits, but almost 1,000 of them are people who stay less than 10 seconds. So it means that people are impatient, they don't have much time, and if you want to help them with your website, you really need to be thinking about how should I design my website. Of course, which content should I put, but also how can I change the design, the overlay, and so on. But of course, you also have 1/3 of the visits that are longer, including quite long visits. So for these users, I think we're doing a good job. But how about these other users? So to summarize, your typical user might or might not be very geeky. She might not have a lot of time to find the information. And anyway, finding the information is hard. Which takes me to the last part of my talk about documentation and teaching. How can you be sure that your package will be useful to users? Because how can you be sure that they will want to use it? And documentation is a very important factor for this. And before I explain how we do the documentation in scientific Python, I'd like just to go a little bit back in time and tell you about my first experience in programming. because when I was a kid, I really was not one of this kid who are always playing with a computer. The first time where I really did some programming was during my undergraduate studies, where I had an experiment. It was a convection cell, and a researcher in the lab was typing some MATLAB comment in a shell, and I was noting down everything in my notepad, and really like it was a book of spells. And after, when he was gone, I was like, okay, what am I doing now? Shall I just rewrite all the instructions? And I had no idea that, for example, you could use one instruction and not the other. I just didn't know how to program, right? Which is normal, because in a lot of curriculum, you don't have programming classes, and I never had one in my curriculum, which is bad, I think. But it means that learning how to program, learning how to do data processing, it's not something that's natural, it's something that you have learned. And because of this hard-fought experience, I think I also feel quite sympathetic to people who are learning tools for the first time. So what is documentation? Good documentation, sorry. I like very much this citation by Peter Hintians. So I let you read it, which is basically telling you that good documentation is not putting comments everywhere in your code. Because documenting code is like writing tasty on the side of a coffee cup. It really doesn't sound good, right? And so it's the API that you need to document. And the good news is that since I've talked a lot about APIs, we've already seen the major part of documentation. It's having a clean, clear, and consistent API. But then it's not enough. And in Python, you have this docstring mechanism that you should use for documenting your API, your functions, your classes. So how do you write a good docstring? Nowadays, it might seem obvious to you, but it was not always like that. So once again, I do a bit of history, because when you go back to 2008, and you take a look at the docstring of one NumPy function, so you had a one-line definition, and that was all, okay? So if you're mostly using modules of the standard library, you might be used to being ill-treated like this. But if you're a scientist coming from MATLAB, for example, you just won't accept this. This is really not helpful enough, and you will just be crying about, I can't find any good documentation. So nowadays it's much better if you compare 2008 to today, because you still have this one-sentence definition, but then you have the definition of all parameters, you have suggestion of other functions, you have a simple example. Okay, I think you all agree that this is much more helpful. So how did we go from this to this? It was not that simple, because when we were in 2008, first of all, GitHub didn't exist. So the number of contributors was quite small. And therefore, there was this idea that a lot of people in the NumPy users might want to contribute some documentation, but that it was hard for them to use this patches mechanism and so on. So the idea came that maybe if we could piggyback what Wikipedia was doing for knowledge, then maybe we could improve the documentation. And this is how the so-called NumPy documentation marathon was created. Because Pauli Virtanen, he set up a website with a wiki where every user could go and improve the documentation, and after it was integrated back into the code of NumPy and SciPy. So of course, nowadays we wouldn't be doing it like this, because we have GitHub, which makes things a bit easier. but at the time it was quite a good idea. And of course, first, before all possible users could storm and write a lot of documentation, we needed to define a standard, because otherwise it would just have become a mess. And therefore there was a lot of documentation on the mailing list about what should be the standard, because there was no standard before, and that is where this architecture with parameters, returns, examples, and so on appeared. And it's, of course, now the standard that you see in most scientific modules. So what was the outcome of this documentation marathon? So the first obvious one is that the size of the documentation increased a lot, its quality as well, because several users were proofreading what other users had written. But it also had a lot of different side effects, and it was a bit like a chain reaction, because there were a lot of new contributors, people who would have never dared to contribute something to open source software, but since it was documentation, it was considered as soft skills, so it's okay, then you can write some documentation. And it also made people quite proud of the documentation, and once you are proud about your documentation, you want to keep it good. And this is really how the standard of documentation was increased for the scientific Python package. So if you want to know more about this whole process, about the NumPy documentation marathon, there was a nice article by Alexandra Porlik, which is accessible on the web, and it's quite interesting to read. And about the number of developers, so I took this graph here from Jake van der Plas' blog, so which represents the cumulative number of contributors to NumPy, SciPy, and Matplotlib. And so what he says is that in 2010 there was a big increase, and he correlates this with the fact that people could use GitHub, which is a very nice tool. So I have the hypothesis that if GitHub is maybe the major factor for this huge increase, the better documentation and the fact that people had contributed documentation and started to contribute might also explain this huge increase. So can I take 5 more minutes, or yeah, okay. We've seen that doc strings are now much better in scientific Python, and nowadays I would say that good and thorough doc strings are the bare minimum that you should demand from a scientific Python package. But it might not be a tool that's good for all users. Some people might want something more holistic, more graphical, and this is where you can use other tools, such as galleries of examples. So I guess most of you have been, at least on the Matplotlib website, when you want to plot a graph and you want to do something specific, sometimes you don't Google for this, you just go to the graphical gallery of example and you look for something that looks like what you would like to do, and when you click, you have the code, and then you learn how you should do it. So that's a very convenient and pleasant way to learn, because it's fast, it's intuitive. And following the Matplotlib gallery, other packages have adopted this way of documenting the package. For example, the gallery of examples of scikit-learn is very nice. And this is something that we also have in scikit-image. So we have the rule now that every time a new feature comes into scikit-image, you need to have a gallery example that comes with it. And this is actually how a lot of users discover what you can do in scikit-image. On the website, 60% of the visits are in the gallery of pages visited. So it's really worth having a good gallery. And well, I guess that at the back you can't see anything, but here is what a typical gallery page would like. So after you have clicked on the thumbnail, if it's something that looks like what you would like to do, you have a bit of explanation, and most importantly, the code that generated the plot, so that you can adapt it to your needs. and start using the functions that you would like to. So I'm really excited to tell you that now it's very easy for every package to create a gallery because of this new project called Sphinx Gallery, which is like an umbrella package for all the possible galleries that you might want to create. And the idea of Sphinx Galleries is that it's a minimal package that you just need to import to create your gallery. And all you need to do is to have scripts with your examples that you want to appear in the gallery. And on top of creating the gallery, Sphinx Gallery also have some nice features, like the fact that it can integrate automatically the examples that you've created on the documentation of a function that's used in the example. So it's a kind of links between pages of your documentation that's very useful, because you might think that if you have information somewhere in the package, it's enough, but you actually need a lot of redundancy in your documentation so that it's really useful to users. And on the other way around, if you go to the code of your gallery example, here underlined, you have the names of functions, and if you click on it, then you go to the API, to the docstring of the function. So the last point that I want to mention is that it's very good to document the functions, the modules, but for a new person who is starting using scientific Python, sometimes he or she will want to understand also how the different packages are linked together. And so you need to organize trainings well, of course, it would be better to have scientific Python classes in universities, but it's only starting. And so I don't know if you know this SciPy lecture notes website, but if not, I think it's really worth checking it out, because it's a website with, I would say, several weeks of tutorials. It's of documentation, but it's really comprehensive tutorials with a lot of examples. And it has a beginner's track, an advanced track, and some more advanced packages. And it's something that was developed and used during the EuroSciPy conferences, and that it's still curated and enriched over the years. We welcome contributions, of course, if you're using the package and you would like to improve some parts. Because at the EuroSciPy conferences, so it's a conference like this one, there is a tutorial track, and every time we train between 100 and 200 people, but it's nice, but it's not something that scales well. And whereas with the SciPy Lecture Note website, every time I have a new student, I can say, okay, you should go to SciPy Lecture Note, read this chapter, and I don't have to organize a training. So it's, of course, it's not exactly the same thing as an in-person training, but it scales, and that's something that's very important. One last thing also is about documentation, is that you might think that we now have a lot of different tools, like with good doc strings, galleries of examples, comprehensive website with tutorials, and that people should be able to learn. But I think it's important to keep on inventing new tools so that people can learn in a more efficient way. And I think it's actually very hard to learn scientific tools, programming, but also scientific tools like image processing. And for example, I find very interesting this auto-thresholding function of ImageJ. So ImageJ is a image processing application written in Java. And when you want to threshold an image, so in scikit-image we have a lot of different functions to do that. But ImageJ has one function which applies all the different filters to your image, and therefore you can pick the one you like best, but also you can learn that some methods exist. For example, this triangle filter. It looks very nice, but I had no idea whatsoever that it existed. So it's a way to really discover by yourself that something is possible, and it's actually one of the most efficient way to learn. So I think I will skip this part on challenges for the future. I might go back to it during the questions. What? Yeah, it's a nice one. It's related to how can we go beyond NumPy, and how can we really keep some consistency, but also have maybe more efficient data processing. And I'll go directly to the conclusion. So during this talk, I've stressed the importance of some good practices during software development. One of them being the APIs. They are paramount. I mean, you can really kill a package with a lot of good content if your API is not good. And the importance of documentation. The message with which I would like to close this talk is also to say that you don't need to be a programming genius to contribute to open source. I've told you that it was actually quite hard for me to start programming, but since I could start by contributing documentation, it was quite easy. And then if you start contributing even a little bit, then you learn a lot, because you have to use the same tools as other more advanced developers, and you also make a lot of friends. So it's actually very nice. And about Scikit-Image, so I'll be around during the conference here. So if you want to talk more about it, to have some information or some feedback, of course, we welcome feedback very much. I'd be happy to talk about it. If you're using, please, cider paper. It's the only kind of credit that we developers get for that. And I thank you very much for your attention.
Any questions? Yeah.
Hi, congratulations for the talk. I was wondering, you cited before OpenCV, and I was wondering what are the main differences apart for the 3D part with respect to OpenCV, and if you are planning to include also some modules for working with videos and capturing real-time movies and so on. Thank you.
Thank you for the question. So you cited indeed an important difference with respect to OpenCV, which is the 3D part. And another difference is that Scikit-Image is not completely a computer vision package. It's more a traditional image processing module. So our users are doing more like filtering, segmentation tasks than automatic detection, for example. But for now, this difference has really been determined by the people who are contributing to the package. And another difference is also that we are a smaller package. I think we have less code than OpenCV, but then we try to have a package that is that has, for example, a documentation that is as clear as possible. So if we select some directions of development, I would say that I would like to have more narrative documentation than new features, for example, whereas OpenCV has already a lot of different features. So I would say that if you're a typical user who is starting doing image processing, you might want to start with Scikit-Image, and then if you need specific tasks that are not found in Scikit-Image, use OpenCV, because you have indeed more advanced algorithms, especially in the field of computer vision. But scikit image might be easier to use if you have not used OpenCV yet. And about the videos question, the answer is yes. We have a few pull requests open on this. The issue is always dealing with the libraries on handling the videos, the streaming, and so on. So it's taking time, but it's planned. Yeah.
Other questions? Okay, so everyone is very shy, or your talk was very good. So let's thank the speaker.